Yeah. You're absolutely wrong.
Yeah, let's
Okay.
Okay, you specified. Yeah. So he said not was here this week, but it will be next week. Yeah. Just like what I
We're
was-
starting our lecture.
We can actually like. Oh, the cool thing you do. It's like a-
Software engineering lecture number 6. And our topic is activity diagrams and class diagrams. Okay. We're going to talk about activity diagrams and class diagrams.
It's there at the bottom.
What is an activity diagram? When we learned the use case diagrams, we said that each use case is a functional requirement. In other words, it's something that some function of the computer. Computer has to do something. What is activity diagram? It is a diagram that shows the sequence of actions. It's funny, there's another diagram called the sequence diagram, but this also shows a sequence that the system performs in order to realize a use case. So you take a use case, but now what are the steps involved in filling it in what sequence are they performed? Therefore, activity diagrams are very closely related to use case diagrams. Activity diagrams belong to the family of dynamic diagrams. What is a dynamic diagram again? Anyone remember? What is it?
Dynamic,
What about it is dynamic?
like represents things that are moving.
Thank you. So here you have behavior diagrams. There's another diagram of diagrams. Structure diagrams, behavioral diagrams, activity, use case.
Great.
And then you have sequence diagram here is interaction diagrams. These are the 3 types, and activity diagram is a behavioral diagram, it fixes the behavior of a system. Suppose we have a class called create account, whose purpose is to create an email account on a mail server. I have to ask myself, what are the actions that the system performs to realize the creation of an account on a mail server? An activity diagram is a diagram that shows all the actions the system performs to realize the use case of creating an account on a mail server. For example,
So what's next?
we're describing the steps that have to be done to do a certain use case. For example, a use case might be creating an account. That's like the most basic kind of use case. And these are the steps. Enter a username. The mail server checks whether the user exists. If it already exists, go to 1. I think that might mean if it. Oh, because you can't create an account if it already exists, right? That's not called creating an account, that's called logging in. Creating it, if it already exists, go to 1 and try a different username.
Yeah.
Enter a password. The mail server checks the strength of the password. If the strength of the password is weak, then go to 4. Enter a new password. The mail server sends the confirmation that the user has created an account. If we reach step 4, then we know the username is available. If we reach step 6, then we know that the password is strong. And therefore it sends a confirmation. Fine. So those are the steps of creating an account. And you see it may use different parts of the system, like the mail server. The steps from 1 to 7 are called a workflow. What?
Activity diagram.
It was also called a workflow of the yeah. What is an activity diagram? Activity diagram is a diagram that shows the workflow of the use case in the form of a picture. In other words, what we just saw was steps, but it's a workflow, but it's not in the form of a picture. So we're going to draw an activity diagram that represents the workflow in a graphical way. So no textual actions, the graphic symbols show it. Now, because people prefer, it's sometimes easier to understand things if there's a picture. So first of all, we got some symbols here. And we have an initial node, which is the starting point. You should really have just one of these. And then the final node looks like a bullseye. You could have more than one of those, because it could end in different scenarios. And then you have an activity in this kind of capsule. And then you have a decision node. This always reminds somebody of a flow chart, because it's very similar to a flow chart. In fact, it's
It's a chart or
kind of like a flow chart. It's like a version of a flow chart.
exactly.
It is kind of exactly a flow chart. Well, it has some added features. Here you see a decision. You can go right or left or down. You have 3 decisions there. A merge node means that in various cases, you come to some common case and then you proceed further. And the arrow in general shows the control flow, the flow lines, like where does control, it's not necessarily data. On some diagrams, like on a data flow diagram, we learned data flow diagrams, right? Did we learn data flow diagrams? I don't remember if we did it yet or we're going to do it. Maybe we're going to do it. We're going to learn data flow diagrams. I don't think we learned them with the circles. We'll learn, no, you did it in a different course. So when we learn data flow diagrams, the arrows will actually show data, what data is passing. Here, it's just a control line, it's just showing who's taking control. And then you have a fork node, which means that as soon as I hit this flat line here, these three actions will occur in parallel. And then you have its mate is a join, which says wait for three different lines of fork flow, and only when they all finished should you proceed further.
First swimming lanes.
Swim lanes, we'll talk about that later. Okay, so here is kind of what I just explained. What these mean. A diamond represents a decision when an activity requires a decision prior to moving to the next activity. You put a diamond between them. The outgoing alternative should be labeled with a condition or what's called a guard expression. You can also label one of the paths else. So here's a funny one in French, but this is receive a video command. And it says receive a video command, and then is the command valid? Question mark. It's not valid. It says command is not valid, then go to refuse the command. And if the command is valid, then go to process the command.
It's an order.
What order?
Command in French means order.
Okay. Command and an order are kind of similar. I order you to listen to my commands. I command you to listen to my orders. After receiving the video command, we ask, is the command valid? So you see, notice that in addition to writing the question on or near the diamond, we write on the arrows the meaning of the two different directions. Okay, clear enough. When is an order not valid, you might ask? In this case, an order, you might be right. Like an order, like you're ordering food from the internet.
Order like buying shopping.
Right, so you're probably right. Yeah, I think you're right, makes sense now with the rest of it.
I am right.
You are right, and you're probably right, and also you are right.
No, I am right.
You're probably right.
It refuse the order
And then it says like this, at least one product is out of stock, so then the order is invalid. I can't make this order. If he asks for pepperoni pizza and I don't have any pepperoni, then I can't give it to him. The product is in the warehouse, but not the quantity that the customer wants. He asked for 6 shirts, so we only have 5 shirts. There's a product that is listed twice or more times. You can't do that. You got to write the same product and then a number by it. The seller does not support the payment method. Okay, for a variety of reasons. Example 2, I go to the ATM and I want to withdraw 200 shekels. Before the introduction code, that is the PIN, in other words, before I put in the PIN, the ATM asks to insert the magnetic card. So we have some kind of introduction code, I don't know, initial code, verification code. Is the code correct? Is the PIN the right number? If it is, then go on to some process over here that says like, give him the money, ask how much money he wants. But if it's not valid, then go back 1 time, 2 times, but on the 3rd times, we don't give him back his card. Maybe if he makes a mistake 3 times in a row, we take his card, he has to go back to the bank. We assume he's trying to trick. So that would be shown in this kind of flow chart, which we call an activity diagram. Here's another one. Enter username. Well, this is actually what we saw before. Enter username. If it's not available, then enter another username. But if it's available, then enter a password. If it's not strong, then enter another password. If it is, then we've created an account. So there you see kind of flow and questions and these triangles indicating ifs. Now swim lanes. Swim lanes are good for answering the question, who performs what action? So the user performs some action. Who performs the confirmation of the email? The mail server. So we might have.
That's you.
Thank you. We might have something like this. This is swim lanes. The same exact diagram, except we pulled it over and we're trying to show what system or class is doing the action. In this case, it's the system called the user, human being, and the system called the mail server. And those, and the checking, the username is obviously done by the user, but the checking of the validity of the username is by the mail server. So you can, a lot of times it's classes. Which class does what thing? Swim lanes can be horizontal or vertical. So in order to better understand the activity diagrams, the activities participating in it can be divided into categories that can be the categories could be who performs the action. The actions before and after a certain activity, step-by-step actions. Each category is named separated by swim lane. Rules on the graphic symbols, the start node, the end node of an activity. An activity diagram will always contain one start node, like I said, but can have multiple end nodes. Like a function, which can have multiple returns. Right, depending on your ifs. Another rule, activity or action means do something. It is recommended that an activity is named with a verb, for example, receive, fill, send, calculate. The arrows for a decision node are called transition arrows. All right, then there's the fork. Here we have an example in French again of some kind of new activity and then receive a video order. New activity, that's in English. But here it says receive command video, a new order from what? From the screen video?
No, video order.
To order a video?
Oh, yeah.
Like back in the day with Netflix.
Or even before with Blockbuster.
Or even nowadays, I need a video like a giraffe dunking. Boom, that's a video order.
Anyway, what you see here is that there's certain activities that occur. If I see this, when does receive a command happen? If I have a diagram like this, when does receive a command happen? Is it after is it after new activity and new activity 2 and new activity 4? Or is it after one of them? So there is no limit to the number of transitions entering the operation or leaving. The exit transitions are activated implicitly at the end of an activity. For example, once the action receive command video send ends, so new activity 3 must begin. When this one finishes, we go to here, we transition. Once the action command video receive ends, the 3 actions 3, 6, and 5 are all activated, but the 3 actions 3, 6, and 5 do not operate simultaneously, and we don't know the order of their execution. Now, this doesn't mean that they're happening at the same time, but they all have to happen, but we're not specifying the order. What about when does this happen? What about the initial ones? So avoid writing an operation with multiple exits because it's confusing. We don't know what the order is. To avoid confusion, there are 3 activities. Are the 3 activities activated simultaneously, sequentially, or conditionally? Use the synchronization bars if needed. Synchronization bar is drawn as a thick vertical line or as a thick horizontal line. Here we see them as horizontal lines. Synchronization lines are used to indicate activity that start together as well as to indicate activities that end together. When you want to indicate activities that start together, use the fork symbol. When you want to indicate activities that wait for the others, use the join symbol. This is the fork, this is the join. It looks kind of like a fork. It goes also this way. Anyway. So do we have an example yet here? Before we get there, when we use the rounded solid regular bar line to represent a fork rotation with an incoming arrow from the parent activity. Outgoing arrow towards the newly created activity. We use a fork node when both activities get executed concurrently and no decision is made before splitting the activity into two parts. Both parts need to be executed in case of fork state. So if we have such a thing like this with the fork, it means that when this is finished, we have this horizontal line. It means we do all three of these things simultaneously. We'll start at the same time only after activity receive command video finishes. But you could also have serial execution. You could have first 5, then 6, then 3. Fork execution with a condition. You could say if there's a certain condition, then do 3. Otherwise, do both 5, 6, and 7. What about the join symbol? This is when concurrent activities converge into one. In other words, we don't do the next thing until all three are finished. In join, the black bar plays the role of a policeman, not moving to the next operation unless all the operations before the black bar have been completed. An activity diagram shows the sequential operations and also the parallel operations, therefore. So here you have activity. This activity then engenders these two activities, but the final activity won't occur until both the two middle ones have finished. If fork and join mode are often used together. Okay. Benefits, activity diagrams have benefits. What are they? They present a number of benefits to the user considering using it. For example, they demonstrate the logic of the algorithm, right? A lot of times, like the flow chart shows you the logic of the algorithm. They describe the steps performed in a UML use case, right? If you connect it to a UML use case, then it explains the use case. Illustrates a business process or a workflow between users, simplifies, improves any process by clarifying complicated use case. Okay. You can add comments with this symbol here. When you want to express the end of a certain flow, you can put a circle with an X inside of it. Flow, final flow. This indicates that the specific flow is ended, but not the entire process. Sorry, you know, that you get a certain flow that does something and then just stop. The process continues elsewhere. If all the different flows have come to an end, then the whole process is obviously over. So here you have activity 1, and then activity 2, 4, and 6 are having in parallel with activity 3 and 5. And they each end, and the flows both end. We don't know exactly when the program finishes. Oh my God. Here's another case where this is kind of weird, because if activity 8 finishes, then the whole program finishes, and presumably we could be still in the middle of activity 4. Kind of. This means the whole program ends. Here's an example in Hebrew. Well, what is this? What kind of diagram is this? What kind of diagram is this, everybody? Called the use case diagram. Now, we can take part of that use case. Which part are we taking? You bought a subscription. Where is that? Here, this one, the one that's in a box. You bought now buying a subscription inherits from buying a card. And it also includes going to, ordering a ticket for a particular concert. So it says here. But see, this doesn't tell me what to do, how this is done. So this will tell me that. So first, display the types of subscriptions a person get. Maybe they get a monthly, yearly. Then sell him the subscription, and then come to a decision. Is he paying in cash or card with a credit card or by check? And then go to here. This is a merging node. So no, this is what do we call it? We called it a joint merging. Merge node, yeah. Merge, not join. Join is for this. Merge node. I call it merging node, whatever. Merge node. So here we have a kind of a weird case, which is a merge node, which also has a decision. It's also a decision node. Because we merge and then we go to be paid, but we also have a decision that if he didn't work, then he comes back and he has to choose again what type of payment. If somehow the credit card didn't work. And then he puts in his details, and then we create his subscription. Like that. There's another diagram. This is like if you have a school park and you have like all kinds of machinery outside and you have to check it, see if it's working. So first of all, you get a list of all the school, equipment, playground equipment. And then you ask the question, are there any to be checked? If yes, then write a report that it works. Doesn't work or start, if it doesn't work, then you have to put a sign on the mitkan or somehow cancel that mitkan. Say that this equipment doesn't work. And if it does work, now check that it follows all the standards, all the the city standards, that it's not, the swing is not too high or etc. Okay, you get the basic idea. Go on. Here's a swim lane where you show, you take an activity and divide it up into, here you use swim lanes not for what class does something, but for what state of the advancement of the whole project are we in. In other words, this is step 1, step 2, and step 3. So you could have swim lanes like that also. Okay, now we're going on. That's enough for activity diagrams. Now we're talking about class diagrams. You guys learned class diagrams already, right? But we're gonna, I think, go into a little bit more detail than we did there. For example, dependency. You have, let's say you have 2 classes in your program, and they're dependent on each other. What does it mean to be dependent on it? What does it mean for a class to be dependent on it? You already studied it, maybe you can answer. What does it mean that a class is dependent on another class?
It needs it for one of its methods.
Well, how do you know, how does that manifest itself?
As an argument, for example, for the method.
Oh, very good. Very good. So let's see what we have here. First of all, dependency is noted like this, which means that A needs B. A is dependent on B. So there are 2 examples when we have simple dependency. Class A has at least one method with one parameter type B, just like that from set. What's another example?
the critical part of class A is class B. Is a class B instance.
Yeah, there's an instance of it, so here. Class A instantiates at least one object of type B in a method, but not in the class list. If it would have it in its in its attributes, then it wouldn't be simple dependency, it would be association. This is dependent, the names are, in my opinion, backwards, but dependency means it's the weakest form of connection. The weakest form of connection is dependency. Association is higher, is a stronger connection. So basically, either it's in a function's parameter list, or it's in a function declared as an instance is declared within the function. In both cases, A is dependent on B. A is dependent on B because you can't have A without B. If I would delete B from my code base, then A would break. If the definition of B is removed from the source code, A will break. If B's behavior changes, also A might break. I may require, I'm dependent on it, I want to use a certain aspect of it. Okay, so here's some code for that. So you have class A, and you have that in his method, he has something of type B. Or in his method, he not in the parameter list, but he actually creates an instance of type B and uses it. So that's dependency. What did I write over here? A. Well, this is how I would call it. See, if I want to call method 1, I have to give it something of type B, so of type B. So I would write a.method and then give it a B. But in 2, I wouldn't have to give it anything, it would create it. Okay. Incorrect Java implementation. This is wrong. Why is this wrong? Well, because here, why is this not called association and not called dependency? I mean, you can do this, you can have class A with an instance of class B in it. But this is another relationship called association. But it actually has it like that. That would be if a person said, I want it to be dependent, then you shouldn't do this, you should do the other. So what about association? Association is drawn with a solid arrow. Remember that we saw here dependency with a dotted arrow. Association is with a filled in arrow because it's a stronger connection. So the line is thicker. Now, in this class, in the above, class A1 maintains a unidirectional associative relationship with class B1. This is also called a navigation because it goes in just one direction. It tells you which way to go. Association is a tighter connection between two classes, therefore we replace that on a solid line. Class A contains an attribute, which is a pointer or handle to an object of type B. Like we saw in the example that I said was wrong, now all of a sudden it's right because this is association. But the B class does not contain any attribute of type A. In other words, class B does not know that class A exists. So that would be like this. See, class B doesn't know anything about A, but A has an instance of B. And you may have a get function to get to B that's in A. So A is dependent on B, but B is not dependent on A. You could imagine a case where it's both directional, where A has an instance of B and B has an instance of A. Where might that be? Well, think of this, that's actually what I've read. That's actually the most common type. For example, every student has a teacher, and every teacher has a student. If you're a student, you're not a student if you don't have any teachers. And if you're a teacher, you're not much of a teacher if you don't have any students. So each one has access to the other. And what does that mean practically? It means if I have an instance of a teacher, I could get a list of all the students that he has. I could use teacher.get students. I would tell me all the list of all, and a student I could give me a list of all his teachers. They all have access to each other. That would be a bidirectional associative relationship. And here you see how you draw it. Not with 2 arrowheads, but with no arrowheads. So this class A contains is a pointer to an object of type B, and class B contains attribute as a pointer of type A. Now, it's a little bit dangerous to use the word pointer because in Java there are no pointers, and yet you can still do an binary, association in Java. So it just means an instance in Java. Here you see, this is a Java example, there's no pointers. So you see that we just have class A inside of B and class B inside of A. And like I said, a good example is a teacher and students and teachers. Oh, here we go. Example 1, student class and instructor class. Every student has an instructor and everything. Also doctor class and patient class. Every patient has a doctor and every doctor has a patient. Student class and university, student class and university. Every university has students and every university student has a university. Could be a first grade student doesn't have a university, but. Now we're moving on to other relationships. Yeah.
Could you say that, angry associated relationship is also dependent or not? Doesn't include.
Yes.
Yeah,
Associative relationships are like super dependent.
so if I was describing.
But if I asked if it has a. What? But if I gave you this example and on a test you wrote dependency, that would be wrong still. Because you have to be specific. It
So
is,
then I don't-
technically, it is a kind of dependency, but it's called an association, it's not called dependency.
If I was asked, this should have no dependency, that means also association then?
Yes. Yes. Aggregation and composition, not in the material taught in the second semester, but it is in our material. Wait, is it? Oh, no, it's not. I took it out. Yeah, it is stupid. They took it out. You know, well, what happened last year was they took it out. And I said, you really want to take it out? We should do it. They said, yeah, it's taught in the next year, in the next class. And I said, well, anyway, it's part of the subject. Let's just teach it right now. It takes 5 minutes. They said, no, it's for the next one. Then when they wrote the exam, they asked questions and I talked about it.
Cool.
I was like, and I told them, you can't have this question. And they ignored me.
They ignore you? My man?
So, but we're not gonna, anyway, I'm writing your exam, so remind me not to put it on the exam.
Unless we were.
What?
Unless we're.
I think I took it out of the slides, so it's out of the slides. I'm not gonna teach you without the slides. Okay, multiplicity, but it is another topic, aggregation and composition. Like, for example, I'll give you an example. Well, it's actually a very interesting topic, aggregation. Aggregation is when the pieces can live independently. Like, for example, the tire of a car may have a certain usefulness without the car. You make a swing out of it. You could, it's not necessarily, you may collect them. As opposed, so therefore we call it aggregation. A car is an aggregation of pieces that maybe each one has a composition means that that the minute the body dies, all the pieces are irrelevant, like the human body. A human, if a person dies, all of his organs are, useless at that point. So that's composition versus aggregation. And so it has to do with the life of the instance, who deletes it, who created it, and who deletes it. When does the delete occur? Anyway, multiplicity, meaning the degree of multiplicity is the number that appears on each side of the relationship. Okay, this number indicates the amount of objects involved in the relationship. If you do not specify the degree of multiplicity, then it's 1. So 20 could be in multiplicity, or 0 to 1, or 0 to infinity, or 1 to 3, or 1 to infinity, or an asterisk. It could be any amount. We have a picture. It would basically mean, like, if I had a picture like this, it would mean that, well, imagine this was not an arrow, but not an open arrow, but a regular arrow, not a square, not a hollow arrow, but a regular arrow. Then it would be what relationship? If this would be
Association.
then it would be association, exactly, in navigation, it's one directional association. And what if I wanted to say that in A, that A is dependent on B because he's got two B's in it? So then I would write 2 over here. I would write 2 over here to say that there's 2 instances in him of B. He's got, let's say B is you know, a leg, and he's got 2 legs. So exactly 2. 2 instances of him. I could say that would be multiplicity. And if it would be a straight line, which would indicate association that's bidirectional, then I could have a 2 and a 2, and then each one has 2 of the other, for example. Infinity would mean that he doesn't have infinity, it means he could potentially have infinity. So if I would want to say that he has a list, if I wanted to say A has a list of B's, then I might write, you know, a star here to indicate as many as I want, because it's a list. It could be a list of a lot of things. So that's the multiplicity. Now we're talking about inheritance, which you also probably saw. What does this mean? Notice that the arrowhead is not, see, we saw before that the arrowhead was just a line, but here the arrowhead is a hollow arrowhead. What does that mean? It means inheritance. What is it? So what does inheritance mean? Who inherits from who in this picture?
A2 inherits from B2.
A2 inherits from B2, exactly. Which means what? Which means all the qualities of B2 exist in A2, but A2 has more things. So therefore, sometimes it's called a specification, or you know, or B could be called a generalization. B is a generalization. You know, for example, you could argue that there's no such thing as an animal. There's a rhinoceros, and you can't see an ant. Nobody says 3 animals came down the street. You know, it's a human concept, an animal. It's a generalization that we derive from actual things. You say an elephant, then I know that an elephant and a rhino and a hippo came walking down the street. I understand. When you say 3 animals, it's like, but you're not saying much. What does it mean? Two ants and a cockroach? So you actually call inheritance generalization or specification. In other words, you could say that B is a generalization of A, and A is a specification of B. So you draw that in Java like this. Class A extends B. B is the generalization. So class B is this superclass, and class A is this subclass. Just remember, the inheritance symbol creates a line from the superclass from the subclass towards the superclass with a clear triangle at the top of the arrow pointing to the superclass. So here you have a nice picture. This means that every credit card account is a bank account. It's called an is-a relationship, actually. And every savings account is a bank account. But there could also be a bank account or not. Notice this is generalization, specification. If you're looking upward, then it's a generalization. There's bank account is a generalization. If in your system there were no bank accounts, there were just savings accounts or credit card accounts or checking accounts, but no general thing called a bank account, and yet I had a picture like this, then we would call bank account, well, we would call it an abstract class, right? That's what you learned. You'd also could call it in Java, I think you would call it a interface. Not an app. They don't use the term abstract class, they use the term interface. Because it's an interface, it just tells you how you're supposed to relate to this thing, but it's not implementable. All right. There's a connection called notation of the realization. Notation of the realization relation. So here, you see it says the word interface? That's exactly to indicate what I was just saying. that B, in this case, B3 is not implementable. In other words, it's not, it's like, you can't have instance of it. You have to realize it with A3. There will never, it's completely abstract. You'll never actually have in your an instance of B3. But yet you want to have it existing for the purpose of inheritance to sort of find the common features of a bunch of other classes. So you, in Java, you would write it like this: class A3 implements B3. B3 being the superclass. See, here we said it extends the superclass. Because the superclass exists. It exists and I can extend it. Here, I'm actually implementing it. It was unimplemented. It couldn't be implemented until now.
You can't write extents.
No. No, you can't write extends if it's an interface, no. This is Java. You didn't know if you learned Java.
You're supposed to be.
I'm doing Java right now.
Doing it, I think.
Oh, we have, yeah, JJ.
You're supposed to be learning it?
We're doing a project, we're doing a mini project, good job.
So here's some details of the language that you may not have seen.
I never did that, so.
These are just details. I mean, otherwise the language is, yeah, it's pretty similar. Here's an example of a realization with an interface. Implements the class implements the interface, right? Printable, A6 implements printable. So here's printable. It's as a void function called print, but the function is nowhere implemented in printable. It's an interface, right? Interface printable just tells you the interface. That's the point. It tells you that there shall be a function called print, and it shall take no parameters, and it shall return nothing. And then that's why it's an interface. It tells me how your class, what interface should there be in your class? Your class, if it wants to inherit from printable, needs to have this implementation, this implement. How you do it, up to you. So in this case, his print just prints out hello. So now A6 is implementing printable because it has that. And now I can create something of type A6. I couldn't create something of type printable. And then I can say print on it. Now I can write a function that takes something of type printable. And as long as and it can take any parameter, as long as that parameter is an interface, is an implementation of the interface printable. Realization of the degree of plurality in the Java language. I don't remember these slides from before, but I guess they were there. So here we have class B1 and class A1, and you see that A1 has an array of B1s. Like I said, it's like a list. And we give it an index, and as a function that returns the index, fine. So you see that this is multiplicity in the sense that, you know, I don't know, infinite multiplicity. Disadvantages. Oh. Dealing with an array is complicated. We have to reallocate the array every time a new item is added to the array. Because if the array starts off as 1, then we have to reallocate to 2. We need to check the range of indices before you access the array. You can't just let him type any number. And notice this implementation is kind of lacking because if he would give us 75, we would just give the 75 without even checking bounds. We should keep track of the bounds of the array and not let him take an element beyond the bounds. Although I think in Java there is automatic array bound checking. So you wouldn't have to do that really, but in C++ you would. Re1 method is not well written. You could get a runtime error if he gives you an out of bounds number. I mean, that's the point, you get an error. Even if Java checks for it, so now you write 25 and it's beyond the size, it'll give you a runtime error. Compile fine, but when it runs, it'll say there is no 25. In other words, In C, you wouldn't get a runtime error, you would just get some garbage, you would just get some number. But in Java, it checks and it would tell you. Runtime error, you've gone out of bounds. So you could try and catch, you could. Or you could check the number ahead of time. You know guys what try and catch is, right?
Yeah, yeah.
We need to check the range of indexes before you, right? Okay. Step 2. That's it. See, with no questions, we go very quickly.